right, good afternoon. Again, just looking at one-to-one functions and their inverses. And we have from page 365, okay, we have a group of functions. And starting off, okay, just some things to mention, okay, for one-to-one functions and their inverses. And there is a rule of thumb again. And this is going to be where we have inverse functions will compose together as x. And for what we have in the problem set from page 365, we're looking at determining whether, okay, the pair of functions will be those that are inverses of each other. And for the functions we have presented, okay, we have the first, okay, whereupon we have h of x is equal to 7x minus 3. And the other one we have is k of x is equal to x plus 3 all over 7. And again, if these functions are inverses of each other, then they will compose together as x. And it's been a while since we've looked at compositions, okay, between two specified functions. Okay, now for one composition, if I have it where h is composed with k of x, and if I put together, someone would be looking at h of k of x. Okay, so k of x is going to be the input function, and the output is going to be in line with that which we have for h. Okay, so looking at specifying, okay, so h of k of x, okay, that is going to be h of, and we have x plus 3 over 7. And operating in line with h. Okay, so we have from h of x, we have h of the input is equal to 7 times the input followed by the subtraction of 3. And for this specific instance case, so we have 7 times the input is going to be multiplying 7 and the ratio x plus 3 all over 7, and then we have followed by the subtraction of 3. So looking at what we have in the mix, okay, so we have 7 times x plus 3 over 7, and we can have the 7s to go out. For which we have x plus 3, and then following we have the deduction of 3. And that composition reduces to x. Okay, and if I reverse, so if I have k composed with h of x, okay, so I have k of h of x, and with h of x as the input, okay, so h of x we have 7x minus 3, and we have operating in line with the output, which we have in the form of k. Here we have k of the input is equal to the input plus 3 divided by 7. Okay, so we have in the follow through. Okay, so for the input plus 3 all over 7. Okay, so the input has 7x minus 3 followed by the addition of 3 all over 7, And if I gather together, okay, so you have 7x minus 3 plus 3 all over 7. And we'll have the negative and positive 3 to cancel out. So you have 7x all over 7. And that also reduces to x. Okay, so both of these compositions reduce to x. And so for what we have in consequence, okay, is yes, they are inverses. Now for what we have in the case of the next pairing, and we have for number 34, okay, now we got our functions assigned at, yes.
I just have a quick question.
Uh-huh.
If you do the first h of k and it reduces to x, do you have to do the k of h? Like if one is, does that mean that they both are, or is there an instance where one is and one isn't?
I haven't run across one that isn't. I'm just sort of checking the consistency, make sure I didn't make a sign error or a mathematical error. So it's like, why is one X and the other one not? I must have made a mistake in the first one, something like that. But if you have, I'm just checking for a consistency. In other words, make sure I'm not leading up to a self-contradiction.
Okay, thanks.
But if you've got confidence in the first trial where it's equal to X, it's pretty much the green light that, yeah, they are going to be inverses. And for what we have in the case of 34, okay, so we got p of x, and that one we have at -3 plus x all over 4, and we have q of x is equal to 4x minus 3. And see if these will compose together as x, and you can go with either route. Okay, and we'll say that we have p composed with q of x. The order does not matter. You can have p on the outside, q on the inside. But with this arrangement, okay, so we've got p of q of x. And specifying, so q of x, we have a 4x minus 3. Again, just in terms of how to go about treating 4x minus 3, again, we're going to operate along the lines of the function p. So p of the input, you have -3 plus the input all over 4, and with the input at 4x minus 3. So we're going to have -3 plus the input, which you now have at 4x minus 3. And we have all over 4. And looking at what we have in following through, okay, so we have -3 plus 4x minus 3. And notice we're not going to have any additive inverses in cancellation like what we have with negative and positive 3 from k composed with h. What's going to arise here is that we got 4x for the variable term and -3 and -3 instead of canceling. Okay, that will go to -6. And for what we have in terms of the follow through, okay, so we got 4x minus 6 over 4, and so I can just split this up. Okay, so you have 4x over 4 minus 6 over 4. Now 4x over 4 goes to x, and negative 6/4, that will go to negative 3/2. Okay, and since that composition goes to x minus 3/2 instead of x, so x minus 3/2 and x, they're not the same thing, and you don't even have to do the other composition because of any of them. If you have a reduction to where you have anything other than x, or whatever the input variable is, it's going to turn out that the functions are not going to be inverses. So while 32 has a pair of inverses, 34 on the other hand does not. All right. Now, looking at again into determining the inverses of one-to-one functions, and we have for the case in number 41, okay, we have in this case we have a given rational function where we have that f of x is equal to 4 minus x all over 9. Okay, and now it's not asking for the domain and the range, but I just want to go ahead and kind of get things squared away. Now if you notice, for the domain by definition is the set of values in the input, in this case the variable x, such that the whole expression will be defined in the real number system, and I have x solely in the top part of this fraction and not at the bottom, and I can have a 0 numerator as long as I do not have a 0 value denominator. Okay, so x can be any real value, whether it's 0, negative, or positive. So for what we have in the case, let's say for the domain of f of x, okay, we don't have any restrictions for x. So the domain is going to be the set of all real numbers. And guess what? In the case of the range for the y values, if I have highly negative values of x, I'm going to have negative values in y. And if I get the right value of x, where I have a 0 numerator, where your y value is going to be 0. And if I have values of x that create positive values, we're going to have y to be positive. Okay, so in their own capacity, the x's and y's will run continuously from negative to positive. Like we have in graphing, you can have the function to run endlessly from left to right, whereas in the case of vertical motion, you have running up and down simultaneously. And the reason I'm bringing this up is that, just to restate, from the perspective of working with the inverse function, it's going to turn out, and I have not attained the inverse yet, but you have going hand in hand whatever we have in x in the one-to-one function, we're going to have in y with the inverse. And it'll also work the other way around. Okay, whatever I have in y for the one-to-one function, I'm going to have in x for the inverse. Okay, so what is in x for one will be in y in the other, and vice versa. All right, so we have both sets of domains and ranges will be all real numbers throughout. And for what we have in the case of the determination of the inverse of f of x is equal to 4 minus x over 9, Again, just setting the stage for the determination of the inverse. Okay, so f of x, okay, again, that is a functional notation for what we have here with y is equal to 4 minus x over 9. And then, once again, just setting things up in the determination of the inverse. Okay, so if I interchange x and y, okay, so what was y becomes x and vice versa. So we have the x is equal to 4 minus y all over 9. And again, I'll be looking at solving for y to determine, okay, just what the inverse will be. Okay, so right now, if I multiply the equation by 9, okay, so we have on the left-hand side of the equation, okay, so this will be 9x. Right-hand side, okay, 9s will cancel out, so I have 9x is equal to 4 minus y and if I isolate, okay, the y term, we have, upon taking 4 away from both sides, okay, right now we're going to have 9x minus 4 equals negative y, and then just writing in terms of positive y, I can just change the signs of everything, whether it is through multiplication or division by negative 1. So if I just change the signs, so we have negative 9x plus 4 is equal to y. Okay. So the implicit layout, okay, for the inverse function, we have y is equal to negative 9x plus 4. Again, we start out with f of x is equal to 4 minus x over 9. And just for the explicit presentation of the inverse, again, so this y that was discovered, okay, this will be referencing the inverse of f of x is equal to negative 9x plus 4. And those are composed together as x. And if they compose together as x, okay, you're going to have the graphs of these items to run symmetrically with respect to the line y is equal to x. And just taking what we have, here we go. Okay, so we got with the graphs. Okay, so you have y is equal to 4 minus x over 9, and y is equal to negative 9x plus 4. So for the given one-to-one function, okay, we have represented in this grid pattern by the red line here among the ordered pairs that the function passes through. You have negative 5, 1, 4, 0, and 13, negative 1. And in the case of the inverse, we have like y is equal to negative 9x plus 4. Okay, you have for this black line, you have the inverse, okay, of the x and the y values from the one-to-one function. So we have 1, negative 5 in contrast to negative 5, 1. And where the one-to-one function has an x-intercept at 4, 0, the inverse has a y-intercept at 0, 4. So again, switching the x and the y, and again you have negative 1, 13 to counter 13, negative 1. And again, both of these graphs will mirror each other about the line y is equal to x. All right. Now, okay, so we have again, so you have linear functions, and as long as you do not have a zero denominator, okay, you're going to have all real numbers throughout for all the domains and the ranges. Now, just sort of changing things up a little, and we have from number 43, okay, we have function k of x, and this is given as a cubic root, whereupon we have that k of x made that h of x. Okay, so you've got h of x, okay, so you have is equal to the cubic root of x minus 5, okay. And I'll just mention now, you have, in the case of the type of root, remember we've got an odd root, as opposed to an even root. Okay, so since we have an odd root, okay, that means that for what we have regarding x, okay, there'll be no restrictions on the domain. So for what this is going to mean, okay, since you don't have any restrictions, that means that for the domain of the function, okay, because you're going to have that h of x this time around, you have the set of all real numbers, and likewise the range. You have positive and negative values at the extremes, okay, for the y, and again. So that means if we have all real numbers, okay, for the domain and the range of the one-to-one function, we'll have the same thing for the inverse. So have all real numbers throughout. Now, in looking for the inverse, okay, so we have starting out, okay, so you have h of x is equal to the cubic root of x minus 5. Again, we have putting in x, y coordinate system terms. Okay, so you have h of x is y. And we have is equal to the cubic root of x minus 5. And again, setting the stage in the determination of the inverse. So if I interchange x and y, once again, so we have the x is equal to the cubic root of y minus 5. Okay, and again, I'm looking at solving for y, so I can cube both sides of the equation. Upon doing so, we have x cubed is equal to y minus 5. And getting y by itself. Okay, so if I add 5 on both sides, so we have the x cubed plus 5 is equal to y. Okay, so we have in the implicit version, okay, of the inverse function, okay, so we have that y is equal to x cubed plus 5. And again, with the explicit notation, just referencing the h of x, that is the functional notation. So we have for the explicit, okay, we'll have for the inverse, okay, this y is going to be referring to, okay, the inverse of h of x is equal to x cubed plus 5. Okay, So both the radical function and its inverse, where we have, in essence, y is equal to x cubed plus 5. Again, we have all the domains and the ranges will consist of all real numbers. And looking at what we have, once again, from a visual perspective, so we have here, instead of straight lines, we have curves. And now, so for what I have in the lower graph, okay, that is in red. This is in reference to the one-to-one function where we have y is equal to the cubic root of x minus 5. Okay, and again, we have just among the ordered pairs, you have 4, -1, 5, 0, 6, 1, 13, 2. And with the inverse, you have y is equal to x cubed plus 5. And again, you have the reverse of these ordered pairs where we have -1, 4, 0, 5, 1, 6, and 2, 13. Okay, just to name a few of the many ordered pairs that are inverted. And again, just both of these graphs, again, they will be proportional and will mirror each other about the line y is equal to x. All right, so we have with these functions, okay, we've had the domains and ranges to consist of all real numbers throughout. And now for the next item, we'll have something that's not going to exactly have that luxury. And for what we have in the case of 53, okay, now this one is a bit analytical, especially if you're looking for the domain and the range. And it's going to turn out that for 53, in a sense, you're going to have the domain already provided. Now we got the function f of x is equal to x squared minus 3. And we have imposed the condition that x is less than or equal to 0. So for what we have in this particular layout, okay, so you have x is less than 0, and that's going to be, in essence, your domain, or the inequality that defines the domain. Okay, now looking at what we have, okay, just looking at a bit of a quick sketch of what we have for f of x is equal to x squared minus 3, and where we have the values of x limited to those less than or equal to 0. So anything to the right of the y-axis, okay, will not exist. Yeah, for what we have here, okay, so you got something starting from x is equal to 0. You have like 0 squared minus 3. Okay, so that's going to be a -3. So you have 0, -3. And if I go to anything less than 0 for x, say if I go to -1, the square of -1 is +1 minus 3, so I have -1, -2. And if I go to x at -2, square of -2 is going to be 4, take away 3, and we'll have 1. So I have -2, 1, -1, -2, and also with the bottom order pair, so we'll have 0, -3. And looking at what we have in graphing, okay, so everything in x will be, if it's not on 0, it's going to be to the left of 0. Okay, and just a couple of things here. So you got x is less than or equal to 0. If you notice from the graphing perspective, you're going to have the minimum y value. Is going to be at -3. Okay, everything else is going to be above. So while x is less than or equal to 0, we have simultaneously that y is greater than or equal to -3. And this is going to be referencing the range. Okay, and just some things to mention. Okay, so we've got in this particular setup, that's when we had the reconfiguring of the domains and the ranges. Okay, so we're not going to have all real numbers throughout. Okay, so we got f of x, x squared minus 3 whereupon x is less than or equal to 0. Okay, so for what we have in the domain part, we got x is less than or equal to 0. So here in interval notation terms, we have going from -infinity and approaching and including 0. And the range of the function we have in reference to y. So we have y is greater than or equal to -3. And so we're looking at starting from and including y equal to -3. And everything else is going to be above and running continuously out to infinity. And again, just restating what I have in y for one and what I have in x in the other, and vice versa. Okay, so so the domain of the function have values of x less than or equal to 0, but for the inverse, it's going to be all values of y less than or equal to 0. And what I have in y for the one-to-one and what I have in x for the inverse. So the inverse function is going to have its domain to consist of all values of x greater than or equal to -3. So I have all the domains and the ranges laid out before even getting to the inverse. And now, looking at what exactly the inverse function is going to be. Okay, so we're starting out with f of x equal to x squared minus 3. Then we have that x is less than or equal to 0. And just putting f of x in terms of y. So we have y is equal to x squared minus 3, whereupon, again, x is less than or equal to 0. And if we look at interchanging the x and the y, so for what I'm going to have here, so I'm going to have that x is equal to y squared minus 3. And the limitation I had imposed for the one-to-one function with x is less than or equal to 0 in the inverse, the counterpart to this is we're going to have that y is less than or equal to 0. Okay. And after the interchange, if I take what I have and write in terms of y equals, okay, so I can isolate right now what is y squared upon adding 3 to both sides. So right now we'll have that x plus 3 is equal to y squared.
Okay.
And let's go ahead and switch the order. Okay, so we say we have y squared is equal to x plus 3. This is going to be your expression so far. And again, we're looking at the y values limited to where we have only those less than or equal to 0. Now, with y squared, if I go from y squared to y, again, you had that square root property of equality, where if I go from the square of the variable to the first order, we have the expression on the other end. We'll be taking the positive or the negative. Okay. So we've got plus or minus. Now there's going to be a tiebreaker. And what I mean by this, okay, it cannot be both positive and negative. Okay, it's going to be one or the other. And the clue to this, okay, is now we've got the y is equal to 0 part if x is equal to negative 3. But for y is less than or equal to 0, we have in the direction of y is less than 0. So for the non-zero values we have for y, those are going to be the negatives. And so we'll have that y is equal to the negative of the square root of x plus 3. And so we're going to have for the inverse so we have the inverse of f of x. Okay, it's going to be the negative of the square root of x plus 3. You don't have to put down that restriction because it kind of takes care of itself. We're just looking at what we have here. Okay, so again, so you'll have interchanging x and y values between the one-to-one function that is given and its inverse, and looking at how the items are going to compare. So this rough sketch was in accordance with y is equal to x squared minus 3 for values of x less than or equal to 0, and to see how this is going to relate, okay, to the inverse. And I'll just mention something too now, just looking at the characteristics. Okay, notice I had imposed that x is less than or equal to 0. So if I had like y is equal to x squared minus 3, I would have had like a parabola that would be mirroring off of the y-axis, where I would be like having a mirroring half, okay, in correspondence on the other side, the y-axis, but instead I'm looking at just the negative values of x, or values of x less than or equal to 0, and you have among the ordered pairs, you have negative 1, negative 2, negative 3, 6, negative 4, 13, and we have for the inverse, notice again that g of x, or y, is equal to the negative of the square root of x plus 3, and then notice I have in the grouping symbols, okay, I have the restriction that x is greater than or equal to negative 3, and that's in reference to the domain. For the one-to-one, again, x is less than or equal to 0. For the inverse, x is greater than or equal to negative 3. And so we have, for the graphs here, again, you have throughout, all the ordered pairs are going to be inverses of each other. Like you got negative 2, 1, 1, negative 2, negative 2, negative 1, negative 1, negative 2, and so on and so forth. And both of these graphs will have symmetry with respect to the line y is equal to x. All right, now, and again, throughout, now there are functions of various types. Like we've had polynomial, rational functions, again one-to-one functions, and also we've had other categories like even functions and odd functions, and then looking at crossing over to different types of operations. And this will be where we're going to be looking at exponential functions. And for what we have in the case of exponential functions and their inverses. Okay, and just a general layout of what I have for exponential functions. Okay, so I have that f of x is equal to a raised to the x. And for this to be a one-to-one function, I'm going to be looking at having a as a positive real value with the exception of 1. And also have in the containment, okay, we have that y, or in this case f of x, is greater than 0. Okay. And let's say that if I were to determine the inverse of what I have here, okay. So again, we just have starting out, okay, so I have f of x so I have f of x is equal to a to the x. Again, f of x is a functional notation for what we say is going to be y. You have the y is equal to a to the x. And, alright, so I'm looking at, again, finding out what the inverse is going to be. So, after putting f of x in terms of y, in this case y is equal to a to the x, now while we have a totally different operation in comparison to what we have had earlier, I'm still going to be looking at interchanging x and y. Okay, so we have the x is equal to a to the y, and I'm looking at expressing this function in terms of y equals. Okay, but now an unusual scenario, okay, is that if I try to express what I have in terms of y, well, we got an obstacle because y is trapped as a power to which the exponential base a is raised. So what I'm going to have to do to get this in terms of y, I'm going to have to do something about the a that is present. And what is the escape route going to be? Well, we have in this particular section, okay, we're going to refer to undoing the presence of exponential bases by utilizing what we refer to as matching logarithmic bases. And so in this case, what I mean by this is that on both sides, so we'll be looking at taking what's referred to as base A logarithm. You have log, then you have subscripted a, so you have this will be read as the base A logarithm of x is equal to the base A logarithm of a to the y. Okay, so I've got the base A logarithm of x on the left. But now to the right, okay, what's going to happen here is that your base A log and exponential base A, they're essentially going to cancel each other out, and anything that is in the raised position as a power, this will be translated to direct terms. So right here, base A logarithm of a to the y that's just going to bring the y down, and that's just going to be the entire right hand side. Okay, so in this case we had that y is equal to the base A logarithm of x, and we have, in the case of the formal inverse, so looking at the inverse of f of x is equal to the base A logarithm of x. And just let me mention some things here. So we had these restrictions. And again, we have regarding a, okay, so you have a is positive, okay, and not equal to 1, and we're going to have that y is greater than 0. But once we look at interchanging, okay, now you're still working with a is positive with the exception of 1, but where we have y is greater than 0 in the one-to-one exponential function, we have for the inverse, we're going to have the x is greater than 0. Okay, so for what we have in the case of the inverse, okay, so you have the base A logarithm of x, and again, as both an exponential and logarithmic base, okay, what we have constricted for a is that it be positive with the exception of 1, and in the inverse, okay, to comply with the inversion of y is greater than 0, the logarithmic expression has to be such that x is greater than 0. All right, and so we got just a question that is frequently imposed, and that is what is a logarithm? Okay, and just by definition, in terms of what a logarithm is, a logarithm is going to be the inverse of an exponential function. And the value of a can come in various forms and applications. Okay. And we'll say that in the case of exponential functions, okay, for those of you who might have had science courses like working with base 10 arithmetic, okay, kind of like acid-base chemistry, like converting like to moles. This is like dealing with exponents and logarithms. Okay, say if you have like determine the inverse. Let's say we have f of x is equal to 10 raised to the x. Okay, and so we have for our exponential function. Okay, so the base a is 10. It is positive, not equal to 1. Okay, so you have f of x is equal to 10 raised to the x. And in terms of the xy coordinate system, okay, so you had that y is equal to 10 raised to the x. And if we look at, once again, interchanging x and y, what was y becomes x, and vice versa. Okay. So you have the x is equal to 10 to the y. Okay. And again, so we have y, again, stuck in the position of being a raised power. But again, just like I had y to which a was raised. And again, just for the escape hatch, I applied logarithms in the base that will match up the number that we have as our exponential base. So in this particular case, okay, the base a is base 10. So that means what? We're going to apply base 10 logarithms on both sides. So the left-hand side, okay, that's going to be a base 10 logarithm of x. And to the right, base 10 logarithm of 10 to the y, that reduces to y. The base 10 log and the exponential base 10, they're going to cancel each other out. Okay, so we have for the inverse, we got y is equal to the base 10 logarithm of x. And just using the inverse notation, so we're going to have the inverse of f of x is equal to the base 10 logarithm of x. Okay, and just kind of show you how the terms or the expressions are going to line up. And so we have a sample of x values. So we have y is equal to 10 to the x. And we have the resulting ordered pair x and y. So we'll say that we have for, first of all, say if we have that x is at 1. Okay. Now for your first y value, okay, so you have y is equal to 10 to the first, which will be 10. Okay, and if I go, let's say to x is equal to 2, or for your y value, you have 10 squared, which is going to be 100. If I go to x is equal to 3, where the y value is going to be 10 to the third, which will be 1,000. And for x at 4, and for y, you can have 10 to the fourth, which will be 10,000. Okay, and so we're going to have for the ordered pairs, it's like we have on an exponential curve. So you have 110, 2 100, 3 1,000, as well as 4 10,000. Okay. So these are samples of points that we have that would belong to the curve, okay, which we have in reference to the graph of y, or f of x is equal to 10 to the x. Now for what we have on the other hand. Okay, so we got with the values of x, and we'll mention now for y. You have a base 10 logarithm of x. Now, base 10 logarithm will exist in your scientific calculator, and you're not going to see the base 10 notation. Instead, chances are you're just going to see log. So log in your calculator is going to reference a base 10 logarithm. And for what we have regarding, let's say the x values, okay, so if I do the reverse, okay, so I have x at 10, x at 100, x at 1000, and x at 10,000. Okay, so we have for the, first of all, for y. So if I'm taking the base 10 logarithm of 10, or log of 10, okay, that's going to go to 1. Base 10 logarithm of 100, think of like 100 is 10 to the second power. So, and just like 1000, 1000 is 10 to the third. Now the base 10 logarithm, or log of 1000, that goes to 3. And that of 10,000 is going to go to 4. So for these ordered pairs, okay, so when x is 10, y is 1. When x is 100, we had that y is at 2. When x is at 1000, we have y at 3. And with x at 10,000, okay, we have y at 4. And if you notice, okay, we have a reverse order of the x and the y values, okay, between what we have for 10 to the x and the base 10 logarithm of x. All right, and okay, so logarithms can apply to base 10 arithmetic, and there's another number of interest, and this is commonly used like say like in not just exponential growth, but also in the realm of finance, among other applications. But I have something like stuff like in physics, stuff like radioactive decay, or I also have mathematical models for population, like population growth, that sort of stuff. And for the number, that's going to be of interest. It's not going to be pi, but it's going to be an entity that is going to have an infinite number of decimal places. In other words, there's not going to be a terminating decimal. And we'll say that just, say for the build-up here, we have like for the items here, we have like x, and 1 plus 1 over x, as well as 1 plus 1 over x raised to the x, Alright, and so we have among the numbers here, okay, so we'll have x at 1, as well as 2, so we have 5, as well as 10, and so we have x at 100, and then we'll say we have x at 10,000. Okay, and we have in the case of the numbers here. Okay, so we have First time, so if x is 1, okay, now 1 over 1 is 1. If I add 1 to this, we'll have 2. Then we have next, if x is 2, we have 1 plus 1/2. I'll just put this down as the decimal at 1.5. If x is 5, I have 1 plus 1/5. In this case, that's going to be 1.2. If x is 10, and we'll have the sum to be at 1.1. And if x is 100, we have 1 plus 1 over x will be 1.01. And say if x is 10,000, well, the sum here is going to be 1.0001. So if you notice, okay, we have a bit of offsetting trend of patterns occurring. So it's where we have x getting larger, and yet the sum is getting smaller. And looking at what we have for the third column, okay, so you have the sum here at 2, the power x is 1. So I have 2 to the first is equal to 2. Now for what we have next, we have 1.5 for the sum. This will be to the second power. And 1.5 squared is going to be 2 1/4. Now for the next, if I have 1.2 to the fifth, okay, we have a number that's a little bit under 2.5. Let's say if I have 1.1 to the 10th power, okay, you're going to have a number that's close to 2.6. 2.5937. Then we have, and then really branching out in terms of the power. Now we've got 1.01 to the 100th. And the output, okay, we have just the change to be such we are budging just a little. And then for 1.0001, okay, to the 10,000. And here we'll have like 2.71814. And notice, okay, when we had 2 to the first, came out to 2. And again, while x is increasing, the sum is decreasing. Okay, and if you notice for the outputs, okay, you have a slow increase as x gets higher and higher. And notice you have the increase. You have basically you're looking at arriving at a saturation point, because you have kind of an increase, and then you still maintain a level of increase, but it's at a decreasing rate. So if you notice, you have between x at 100 and x at 10,000, the amount of change is almost negligible. And now, so and going to this particular number, what's going to happen here is that as x approaches infinity, what's going to happen here is that your statement in reference to 1 plus 1 over x raised to the x you're going to have this statement is going to be approaching a particular letter of significance, and it's going to be the letter E, and this value you have like 2.71828. And some more decimal places, okay, and again, like pi, we will have no terminating decimal. And in terms like what is this base E? Well, for what we have in the case of E is what's going to be referred to as the natural logarithmic exponential base. And for what we have in this particular case, all right, so we got for E itself, I'm just going to kind of give you a rundown. Okay, so if I have determined the inverse, okay, so we have f of x is equal to e to the x. Okay, so e is that 2.718 number. Okay, so you have transition from f of x to y is equal to e to the x and if I look at interchanging x and y, so I have that x is equal to e to the y, and again to free up y, I'm going to take a base logarithm that matches what I have as the exponential base. So we have a base c logarithm in this case. So here we have the base c logarithm of x is equal to the base c logarithm of e to the y. And just switching the order, okay, so you have y is equal to the base c logarithm of x. And you will not see this notation quite so much because here you got, again, so you have e is the natural logarithmic exponential base. And the more common way this is going to be expressed, okay, we have ln of x, so like natural logarithm of x. So for the inverse, we got the inverse of f of x is equal to the natural logarithm of x. So we mentioned, okay, now we have for what you have in your calculator, so you have like log of x refers to base 10 logarithm of x. And if I have ln of x, that's going to refer to logarithms of base e. So you're looking at the base e logarithm of x. So you should have these in your scientific calculator. Again, ln is in reference to e, that 2.718 number. And again, log will be referencing what we have for base 10 logarithms. And now, okay, now where base 10 has many applications in terms of like physics, chemistry, geology, we have like for natural logarithms, and you have somewhat similar applications, and you'll probably see these more frequently in the case of money matters. And let me give you just kind of a rundown in terms of what we have regarding interest and finance. Okay, I'll be looking at 3 categories of finance. Okay, so if we have for simple interest, and what I have here, okay, a couple of formulas here. Okay, you have I is equal to PRT. And we have the A is equal to P plus I. And in terms of what the variables are going to signify, so So A is going to be the amount of interest. And for the value P, okay, P is going to be what's referred to as the principal. And that's going to be the amount invested or borrowed. Or you can just say the amount financed. Okay, and R, okay, that's going to be the rate of interest. And that's going to be as a non-percent decimal. And T is going to be the amount of time. And that's almost always given in the context of number of years. And then we have for this value A is going to be the future amount or the future value. And we have in the next case, right? So these are just formulas for simple interest. And now, in the case of future value, okay, there is one item. This will be with the compound interest formula. You have a lot of the same characters to carry over. You're still going to have the future value A, P, the principal, and you have times the quantity. So you're going to have 1 plus R over N to the N times C. So we still have same R, same P, same R, same T. But now for the new character that we have with N, okay, that's going to be the number of compoundings per year. And just for the descriptive terminology, okay, so you have like annual compounding. We're looking at once a year. If I'm looking at semi-annual compounding, that's like once every 6 months. Or in this case, we're going to have twice a year. And if I up the frequency, say to where we have compounding done on a quarterly basis, we have the N is equal to 4. And for monthly compounding, okay, so you have like 12 times a year. Now for daily compounding, the numbers can vary, but most are going to reference number of typical days in a calendar year. So you have it 365. Though some places might have 360, like using base 10 arithmetic as much as possible. And okay, one might ask, can you go beyond daily? Okay, well, in a sense, you can. All right, there's another way. Say that as n approaches infinity, what's going to happen here is that with our formula, as n approaches infinity, interest is compounded continuously. and we have a rewrite for the formula. Or in this case, the changeover in the formula from this, if we have n approaching infinity, then we have the a is equal to p, and this whole parenthetical expression, so the n times c, that's going to be consolidated or condensed to where we have this expression is going to be e to the r times t. Okay, so these are your counterparts here for the simple interest. You have I is equal to PRT, and the future value is going to be the sum of the amount financed and the interest accrued. And then you have the non-continuous compounding for the future value from annual to daily compounding. And if you have continuous compounding, we had that formula to become A is equal to P times E to the R times T. Again, where E is that natural logarithmic exponential base.